I welcome you yet to another episode of Respiration. I want to thank you who is always following me. I am still your teacher Osbert in Warinda. Now to go straight, in the previous video we were able to see how the pyruvate, after it has entered into the matrix of the mitochondria, how that pyruvate undergoes modification in what we called a link reaction to form a molecule which we named as, or which was called the Acetyl CoA. So after having seen the formation of Acetyl CoA, after a modification of pyruvate, now we go straight to Acetyl CoA, which now comes and enters into the Krebs cycle. So in this video we are going to explore more about what we are going to explore what in details what exactly happens within the Krebs cycle. Now, of course, now we are going to begin this we are going to begin with this Krebs cycle with our acetyl coenzyme A. We are going to begin with our acetyl coenzyme A, which we have got from the link reaction. Remember, the link reaction also occurs in the matrix of the mitochondria. Yeah, but we are saying in the real cycle takes up the acetyl coenzyme A. And then we are seeing that now this acetyl coenzyme A will come and join into the Krebs cycle. Now, what are those molecules within the Krebs cycle? Now, the fastest molecule within the Krebs cycle is what we are calling oxaloacetic acid. Oxaloacetic acid, or you can also call it oxaloacetate. So it will come and find this molecule, which is known as the oxaloacetate. So we shall have here our molecule, which is known as oxaloacetic acid, but of course the better way how we can mention, we should be mentioning it is oxaloacetate. Okay, so we have our molecule here, a compound known as oxaloacetic acid. So it is this oxaloacetic acid, that will be able to join up, or it is the one which is going to be able to join up with acetyl coenzyme A, which came from the link reaction. And of course, this one here is having 2 carbons. So if that one is having 2 carbons, we are going to find out from oxaloacetic acid. For those ones who have done some nutrition, this oxaloacetic acid molecule is also present there within photosynthesis. For example, that is in C4 plants and C3 plants. If you go into the metabolism of C4 plants, you're going to find this oxaloacetic acid there in nutrition. So we are saying we shall have this oxaloacetic acid molecule. This one is having 4 carbons. So we are asking ourselves, if I have a molecule which is having 2 carbons, and this molecule is having 2 carbons is combining with a molecule which is having 4 carbons, so it means the molecule which is going to be formed, this molecule is going to be formed is going to be having how many carbon atoms? They are going to be 6. So it means this molecule is going to be formed that is having 6 carbons is what we are calling citric acid, or we can call it citrate. We can call it citrate or citric acid, but I think let us use this format here. It's going to be called the citrate. So it means this citrate here we are forming it. For it is having 6 carbons. So we have oxaloacetic acid joining up with acetyl coenzyme A and then forming citrate, or what sometimes we can also call citric acid. This is the citric acid, which is the first product which is formed. Remember, we said Krebs cycle can also be called citric acid cycle. Why? Because now this is the first product which is formed. And we also saw that the Krebs cycle can also be called the citric acid. Can also be called tricarboxylic acid cycle. Why? Because we saw that this molecule we are forming here has how many? It has 3 carboxyl groups, and that's why this cycle is also called the tricarboxylic acid cycle, as we already saw. So after having formed this, now we have this citric acid undergoes undergoes other reactions to form other molecules, to form other intermediates. However, because our major aim is to make biology easy, I think for maybe not to cram these names and so on, which seem to be complicated, I think let me give you a small formula that you can follow. What's that formula? I think I've not forgotten. Yeah, there is a formula. However, this formula that I'm giving is just my own formula. You can also formulate yours. And that this formula is trying to give you the molecules which are involved within the Krebs cycle. And this formula is, I can say, all of us, I think we know champions. I can come here and I say that original. Can come here and I say that original champions, original champions kick soccer. I don't know if you know about that game which is called soccer. Maybe I have never played it, but maybe take it as football or what. So you're saying original champions kick soccer for money. For money. I've said this is just my own formula. You can also put yours. In this formula of original champions kick soccer for money, I am picking out the beginning part. I'm picking in original, I'm picking O. In champions, I'm picking a C. Kick, I'm picking a K. And then soccer, I pick a C. Then 4, I pick F. And then here, I pick an M. And now all those letters you are seeing there represent molecules which are involved within this Krebs cycle. Now the first two we have already given them. For example, the O we have taken it on to be oxaloacetate, what you can also call OAA, oxaloacetate or oxaloacetic acid. Now the C is citrate, what is also called citric acid. Altogether, so now the other molecules are what? You know them. Check in that book of yours where you are reading. Yeah, so the other molecule, if it's not citrate, now from citrate now come to K, and this K is none other than what? This K is none other than a molecule which is called, okay, we begin by putting alpha, but the molecule here is alpha keto glutarate. Alpha keto glutarate or alpha keto glutaric acid. So we are calling it alpha keto glutarate. So the K is that keto glutarate. Then from there we now come to the S. So the S, we are going to have another molecule here. The S, we are going to have another molecule here, and this molecule is none other than it is what? Succinate. Yeah, we are going to have succinate here as our other molecule here. So our other molecule is involved here is called succinate. Succinate. You can also call it succinic acid. Manji, succinic acid, or you can also just simply call it succinate. Now from here, now we go on. From there, it means this succinic acid or succinate is going to be later turned. It's going to be turned into what? We now got for F. So the F goes for another molecule, which is called what? Which is called the fumarate, or what you can also call fumaric acid. It is fumarate. Fumarate, what you can also call fumaric acid. Of course, for some books, they even add some other intermediates here, but we are ignoring the intermediates. Yeah, we are going for the final stable products. So the intermediates, we are ignoring them. So we have fumarate. Then from fumarate here, we have the last molecule here, and that last molecule here that we have is the one which is having the M. And this M is also in nutrition, for those who have watched the video about the nutrition in plants. That one we are going to find here, our friend, which is called the malate, like that. So with that, then from this malate, remember a cycle, why it's called a cycle is we should have a starting point, and then we should move, and then finally come back to the same to the same point. So this malate, we shall see it again turning and giving us back the oxaloacetic acid, and then we shall have the cycle begin start again. For example, now this oxaloacetic acid will again combine with the acetyl coenzyme A, and then to form again citric acid, and then the cycle will continue like that. So this is now how the cycle looks like. However, there are very many molecules which we need to include. There are very many things we are supposed to include, but I am going in this kind of stepwise format so that you can easily understand it. That's why I'm moving so like that. So at first, the molecules which are involved, apart from acetyl coenzyme A, which has come from the link reaction, here we have 1, 2, 3, 4, 5, 6 major molecules. And we are saying the formula, we are saying OCKSFM. In fact, somebody was even telling me that we can also call it OCKSFM. That there is a radio station which is called OCKS, then FM. FM is like a radio station, those FM radio stations. So we have OCKFM, but now we are saying here we're just putting our own things to have this formula here. Okay, so after having known these molecules here, then we are saying that these molecules don't just, this one doesn't just from nowhere just turn into this. It means there are some things that should occur to this molecule for it to turn to this. So that's what we want to look at. Okay. Now, having understood this one here, now we have, during this cycle, we have got a lot of dehydrogenation. We have got a lot of dehydrogenation, a lot of removal of hydrogen atoms, hydrogen ions from different reactions. So we shall have dehydrogenation, we shall have dephosphorylation, we shall have decarboxylation, and very many other things as we are going to see. So, for example, if we can begin with the removal of hydrogen at different points, you're going to have hydrogen ions removed. And if we can begin with the dehydrogenation process first, we are going to find out that dehydrogenation is going to be done by two molecules. One of the molecules is the molecule that we have already known for those who have followed me in as far as this series are concerned, and that is the NAD+. So the NAD+ is going to help us in dehydrogenation, in removing the hydrogen. And then we are also going to find, so one of the molecules is going to help us to remove the hydrogen. We are calling it, we are saying that is going to be NAD+. So we shall have our NAD+ help us. However, we are also going to find another molecule, and that molecule is going to be our FADH+. This is going to be our FADH+. So we are saying these are the two molecules which are going to help us to, and I saw these molecules are just nucleotides. These are nucleotides that are going to help us carry hydrogen ions from different reactions here and take them somewhere, and that is none other than the electron transport chain. And then we are saying, if we are beginning with NAD, this nucleotide called NAD, we are saying this NAD is going to help us remove hydrogen in 3 places. What am I saying? NAD+ is going to help us remove hydrogen from different parts, and those different parts are 3, or those different areas are 3. Now, where are these 3 areas? The first area is this one here. Here we have entered. Here the acetyl coenzyme has entered. It has combined with this. It has formed this. So this now becomes our first place. After the entry point, this one becomes our first place. So we shall have NAD+ help us remove hydrogen here. However, we shall also have NAD help us remove hydrogen at this point here. at this point here, and also going to have NAD, help remove hydrogen at this last point here. So those are the three places. The three places we are saying, if this is the entry, if this is our entry place, so we have the first place, second place, and last place. This is our entry point. So if this is our entry point to the cycle, we are going to have NAD, help us remove hydrogen at the first place, second place, and last place. And therefore, this is how we are going to do it. So to show that, we shall come here. We shall come here and show that. So we shall have our NAD. So we shall have our NAD come here. We shall have NAD, our NAD plus. Our NAD plus. Then this NAD plus is going to come into this reaction here. And as this reaction is progressing, this NAD plus is going to help us remove 2 electrons and remove 1 proton. Yeah, these molecules here, actually, they carry 2 things. They are able to carry hydrogen atoms, hydrogen ions, but at the same time, they also carry electrons. And all these 2 are carried and taken to the electron transport chain. So, these NAD and FAD, they are doing 2 functions. They are both electron carriers, but at the same time, they are also hydrogen carriers. So, they are going, as this reaction for this citrate, to turn into alpha ketoglutarate, we must have a removal of hydrogen ions, and also removal of electrons. So in that process, what is going to help us remove the electrons, the two electrons, for example, and the proton, what is going to help us do that work is the NAD. And when this NAD combines with those 2 electrons and the proton, it is going to turn, as I already explained previously, is going to turn into NAD plus. It's going to turn into, not NAD plus, but it's going to turn into NADH. So you can also come and say NADH plus hydrogen plus H plus. Of course, I still repeat how this reaction is formed. I already explained it in the previous video for those who have been following me, especially when we are looking at the glycolysis. I explained how this is formed. But somebody can just take it like that for now. In case you want to know how it is formed, you can go back to the other video and watch how we explain the formation of this. And then we have said NAD is going to pass in that first place. This is the entry place. So this is the first place. We have the second place here. So at this point also we shall have our NAD. We shall have our NAD. We shall have our NAD plus. This NAD plus is oxidized. Once it's oxidized, when it gets the hydrogen, then it becomes what? Reduced. Remember, reduction means what? Reduction means the removal of electron, removal of oxygen, and then addition of hydrogen and addition of electrons. So we are saying this NAD is oxidized, but when it comes here, it's able to get hydrogen ions. And at the same time, it's also able to pick electrons. So it means it becomes reduced. And once it becomes reduced, now the reduced form of NAD plus is this one we're having, which is NADH. So that NADH is the reduced NAD plus. So when the NAD plus becomes reduced, this is what it becomes. Of course, with our hydrogen, with our proton there. Now, of course, our basic, what we are basing majorly is this one here. This is our main concern here. Now we are saying NAD is going to help us remove hydrogen and remove electrons at this point. It's going to help us remove electrons and hydrogen at this point for this thing for this molecule to turn into this. Also at this point here. So likewise at this point we shall have we shall have our NAD plus. We shall have our NAD plus picking the electrons, picking the protons to turn into NADH, of course, plus hydrogen ions, done like that. Okay, so we are saying that that is now for the case of what? NAD plus. Now, if we come to the FAD, to this FAD, now this other also nucleotide, this FAD also is going to help us in somewhere, and that is only in one place. And that, what is that one place? That one place is this one here. This one here where we're having, if you want to understand, you look for where there is F, We see here there is an F. So we are saying in this reaction where we are having succinate turning into fumarate, we are saying that one, the conversion of succinate into fumarate is what involves dehydrogenation. It involves dehydrogenation, and therefore this is what is going to happen here. So we shall have now here FAD help us. So FAD here is going to help us. So this FAD, which is now FAD plus, unlike NAD plus. For the case of NAD plus, once it picks electrons and protons, so that reaction I explained, it will form NADH, then plus hydrogen ions chemically when you go to the chemistry. But we are saying for this one here, when you go to its chemistry and its reaction, for it, it will come pick 2 hydrogen ions and also pick the 2 electrons. And when after picking the 2 hydrogen ions and the 2 electrons, of course, we shall end up forming. This one will end up forming. We'll end up forming our FAD, but now this will be FAD H2. So when you go into its chemistry, we are saying now here it is not like the way how this one was. Here we have FAD plus picking 2 hydrogen atoms. 2 hydrogen ions. So the 2 hydrogen ions first combine with the 2 electrons to form hydrogen atoms. Then the 2 hydrogen atoms will come and combine with the FAD, and then we shall end up having now our FAD H2. So this is what we are having. So we're having FAD plus giving us FAD H2. Here we had NAD plus giving us NADH. Now we are saying this NAD, within this NADH we are having 2 hydrogen. So 2 hydrogen ions, and at the same time we're having electrons being carried within this FAD here. So this FAD is just like the way you have this NAD, it is carrying electrons, it's going to carry electrons, it's going to carry hydrogen atoms, hydrogen ions, and then these hydrogen and electrons are going to be taken to the electron transport chain for further process, as we are going to see. Okay, so we are having, now we are done. We are saying NAD, FAD are helping, they have done their work of dehydrogenation and they are done. So after that, we are also going to go into another step, which is called decarboxylation. I've told you we have decarboxylation, we have dehydrogenation, and we are also going to find dephosphorylation and maybe another reaction, another process we are also going to find there. So what happens here is that we are going to have decarboxylation. And how is decarboxylation going to come in? I already told you that whenever you are doing decarboxylation, here we are losing a carbon, but we are saying this carbon, we lose it in this reaction is by using form of carbon dioxide. So what you are going to do here is that we are going to come and ask ourselves that here this one was 2 carbons. These 2 carbon, this molecule is having 2 carbons. Combined with this molecule was having 4 carbons, and it formed the molecule which was having 6 carbons. And then after having known that, now we are asking ourselves what happens next. So what we are going to do is that we shall say that from here, this structure here, if you go into its molecular formula, you are going to find that this one for it is having 5. So that means the format is in such a way that the 4 combines with the 2 to form 6. Then 6 reduces to 5. 6 reduces to 5. Then 5 we now reduce to 4. And then after reaching 4, we pause there. We don't now reduce further. So it means here we have also 4. We also have 4. And then we have 4. So it means from here to here to here, we're just playing around with almost the same structure, but playing around with hydrogen atoms, because you see here we have removed the hydrogen atoms. We are going to see something happening here. Here we are also now removing hydrogen. We are also removing hydrogen. So it means here we're just playing with hydrogen. We are playing around with the hydrogen atoms within the structure, but basically the carbon atoms are remaining the same. For succinate, fumarate, malate, and oxaloacetate, the carbon atoms are the same. We're just playing around with the hydrogen atoms. Okay, So, so we are saying if we are having 4 and has combined with the 2, we have formed 6. That is understandable. That is very clear. But now, for us to move from 6 to 5, that means we have lost a carbon. And how do we lose that carbon? That means for us to have, for this one to be possible, during this reaction, that means there is a decarboxylation, and within which we lose a carbon in form of carbon dioxide. So we shall have here, we shall have a loss. We shall have here decarboxylation. We shall lose a carbon in form of carbon dioxide. At that point, for us to have carbon atoms move from 6 to 5. Likewise, also here, where we're having 5 carbon atoms reducing to 4. That means we also have a loss of a carbon in form of carbon dioxide. So we shall also have decarboxylation here. So likewise here, we shall also have decarboxylation. We have loss of the carbon in form of carbon dioxide there. Then, what else? Here we have 4, this is 4, so it means nothing. Here they are the same, here the same, so it means we have carbon dioxide lost in 2 places. We have carbon dioxide lost in those 2 places. Why? Because we have a reduction in the carbon dioxide. I mean, we have a reduction in carbon atoms. Then, now I think we are remaining with like a few 2 things. And what are those 2 few things? One is we are supposed to have, remember we are in Krebs cycle, and as I told you, this stage is at every stage we must have ATP produced. So as you are watching, you may ask yourself that in this cycle, I'm not seeing anywhere where ATP is being lost. So why ATP is we should have somewhere where ATP should be produced from, and where is that? That will be the second step here. So on this second step, we have very many things which on this second area here. I told this is the entry point. This is the first area. Now this is the second area. So at this second area here, we have very many things which are happening there. One, we're having dehydrogenation. And what is helping us to do that removal of hydrogen? We are saying it is NAD+. We are having decarboxylation. We are having removal of a carbon atom in form of carbon dioxide. You see? Now we are saying at the same time we have another very important stage, another very important process that should take place within this process here, within this reaction, this series of reactions here, and that is dephosphorylation. That means as for this alpha ketoglutarate acid to turn into succinic acid, also into succinate, there must be a loss. There must be a loss of a phosphate, and that phosphate, as that phosphate is lost, we shall have in the process of losing a phosphate, what is going to happen is that that loss of a phosphate, for it to happen, we shall see that phosphate, after it has been lost, it will combine with ADP. So that phosphate, which is going to be gotten from this reaction, is going to combine with ADP, and we are going to form ATP. We are going to form ATP. Of course, I know some of you want me to write like this. You want me to come and put here that the ADP will react with PI. That's what most of you want me to write. Okay, I've written it, that the ADP combines with PI to form ATP. But here, even when I had written it like this, I was trying to say that the ADP, as this reaction is taking place, we shall have a phosphate given out. Then that phosphate is going to combine with ADP. So this ADP is going to react with the phosphate inside there, and we shall end up forming what? We shall end up forming ATP. But of course, as you read books, in most cases you put here that T plus PI. But what we are trying to mean, its meaning is that in this reaction, there is also this PI is coming from this reaction here. It's coming from this reaction and is combining with ADP to form what? It is reacting with the ADP to form ATP. So we have energy being produced at that point like that. We have got ATP produced there. Now, the question is, teacher, we are seeing apart from the entry point, of course, this entry point here, this is where acetyl coenzyme A is entering from. Now, somebody might say, okay, we have said this here, acetyl coenzyme has entered. Here we have seen dehydrogenation, we have seen decarboxylation. Here we have seen 3 processes take place there. Here we are seeing dehydrogenation by FAD, which is okay. And then here we have seen dehydrogenation by NAD still. Teacher, do you want to mean that at this point nothing takes place? If there's nothing that takes place, then what makes fumarate turn into malate? I will say there is something that takes place here. And what takes place here, we shall call it hydration. So here, there's addition of what? There's addition of water. So what happens here is what we are calling hydration. So we shall have hydration. So we shall have addition of water, and now after addition of water, that's what will enable this fumarate turn into malate, and then the cycle is repeated. So are you seeing there? So now this one that we have got here is what we are referring to as, the Krebs what? It's what we are referring to as the Krebs cycle. That's what we are referring to as the Krebs cycle. This one now we are having here. So, having seen this, now we need to first make some conclusions. Here. Now, what are those conclusions? Come with me in the next episode, and we are going to talk about those conclusions from this Krebs cycle. See you in the next episode. May God bless you.